Sorry, I guess it's better now. Should I start over? Or?
No, speaks it.
Okay. Okay. So, sorry. So okay. I hope everybody could still follow from the slides this introduction. Okay. So technically, how that looks is the following: the dynamics is encoded into Lagrangian, which starts like the one in the standard model, and then is supplemented by the full tower of higher dimensional operators that one can write using the standard model degrees of freedom and respecting the usual gauge symmetry of the standard model. So for instance, one example of operators among many couples, for instance, two Higgses to two fermions. And for instance, this kind of operator in the broken phase of the SMEFT would induce deviations in the coupling of the Z boson to those two fermions. So there are bases which are known, for instance, in this paper dimension 6 and in subsequent papers of higher dimensions. So when you try to make a fit of this, a fit of data using the SMEFT, you have to deal with the fact that you have many new parameters to consider, in particular, given that you have Flavour indices in most of the additional operators. So that's defines a huge parameter space, and usually there are assumptions being made to simplify those fits, for instance, turning on one coefficient at a time, or including Flavour patterns, or turning on only real coefficients. Okay. These kind of assumptions that allow to get more compact predictions and which are then fitted to experiments. Of course, you could ask what happens when you lift some of these assumptions and you do fits with more parameters. And questions that you can ask a priori before doing that is, what is the actual parameter space of these fits? For instance, how many parameters should you include, and which one contribute to which observables? And you could also ask, what are the expected sensitivities to the latter parameter? So for instance, given one SMEFT parameter, how much do you expect that it contributes to this or this observable? So those are questions you could ask. And in this talk, I will ask similar questions with a focus on CPodd observables. So the overarching question, I guess, is what is the CPodd parameter space in the SMEFT? So before I answer that, let me just flash briefly the outline. So I will first review CP variation in the standard model, because several of the concepts I will manipulate can be motivated from here. And then I will discuss CPodd Flavour invariance in the SMEFT. And finally, I will discuss some applications of this framework. Okay, so going back to the previous slide, I was asking what is the CPodd parameter space in the SMEFT, and you could ask, why are you asking this? Such questions are already being worked out. For instance, I dimension 6 in this paper of Alonso, Jenkins, Manor, and Trott for any number of generations. They have counted CP even and CP odd parameter, so it seems like this question is addressed. However, when you talk about CP violation, there are some subtleties that are not directly, that you cannot directly see on this table, although it's of course technically correct. So to do this, I will review CP variation in the standard model to motivate what I'm going to say next about the SMEFT. So let me explain or remind probably to the expert of you, when does the standard model break CP? Of course, the usual law is that the standard model breaks CP because the CKM metric that couples U and D equal to the W bosons is a complex matrix. So depending on, in order to be able to define a CP transformation at the level of the standard model fields that leaves the Lagrangian invariant, that implies some conditions on the CKM matrix. And for instance, one thing that works to have a CP transformation would be to take a CKM metric which has this form, namely it's completely real. In that case, I can the standard model with this CKM matrix, of course, which has nothing to do with the data, but with the point of parameter space of this theory that is the standard model here would not violate CP. However, if I give you a new matrix, which has obviously imaginary parts, you could ask, does this really violate CP? Of course, the answer is not just checking whether you have eyes somewhere in this matrix, because there are manipulations that could still be used to absorb this parameter. For instance, this matrix is equivalent to the previous one I wrote up to these diagonal phases. And that makes it such that all the imaginary parts I see are actually fake. They can all be absorbed in the field. And the proper way to ask this question is not to look at some imaginary parts in the matrix, but to look for genuinely imaginary quantities, namely those which do not change when you rephase the fields in order to absorb such phases. So for instance, in the standard model, the quantity you should consider is the imaginary part of this product of CKM entries, which happens to be completely invariant under the kind of rephasing you could do to absorb this phase. So here, if you compute this quantity for this matrix, you just find that it is 0, and that's enough to claim that CP is not violated for this matrix. Then you can go to another kind of matrix, and in that case, this quantity is non-zero, and you can again ask, okay, this time am I still violating CP? And the question is still not so clear, because this matrix is again related to the first one I wrote up to this matrix here. This matrix has the following form: it's one phase and a 2x2 unitary matrix, and all these can be again absorbed in the field, provided the dynamics has verified some conditions. So in that case, if the two first up quarks are degenerate in mass, one can completely interchange them without changing the dynamics, and I can absorb this whole 2x2 matrix in the Lagrangian and still get the CP conserving field. And that, of course, works for all kinds of degeneracies in the Fermi spectrum. So in the standard model, the actual order parameters for CP breaking has the following expression. So it's the product of this, the imaginary part of this product of CKM elements that we saw before, times all possible differences between masses, or here Yukawa couplings of the different fermions. So in the in the up sector or in the down sector. So if this quantity is 0, then CP is concerned in the standard model. And any of the way of sending it to 0 suffices to make CP concern. And the nice thing about this expression is that it can be very compactly rewritten using the Yukawa matrices. If you now work in the basis where the gauge fields, the gauge coupling are diagonal, so each fields are arranged into gauge multiplets. So now the Yukawa matrices are 3x3 matrices in general. So if you compute this expression, it gives you, for instance, very explicitly in this basis that can be reached via different field rotations, you will recover this expression. And what's nice about this expression, this compact expression here, is that it defines a Flavour invariant in the following sense. So the physics I study should not depend on how I label my fields, and this is encoded in the presence at the level of the standard model of this large Flavour symmetry that leaves untouched the gauge interactions. It has the form U3 to the 5th, and the non-abelian parts transform the different fields in this way. And if I now define the Yukawas to be spurions of this transformation, they all have these properties. And you can check immediately that under the action of any of those groups, this expression here doesn't change. And so it really captures something about the imaginary parts in this model that is completely independent on how I relabel or rotate the fields. So that's and the statement, at the level of the model, which I already stated, is that CP is conserved if and only if this quantity is 0. So that's a useful quantity because, for instance, from such manipulations, you see very easily that CP is not broken in the standard model when there are two flavors, which you can, of course, obtain via other methods, but looking for such expressions show you that there are no possible candidates for a similar expression when the number of flavors is 2. And it also shows, most importantly, that CP breaking is some kind of collective effect. Namely, in this expression, we saw that there are tons of parameters which are involved, and it means that CP is only broken when all these parameters are simultaneously present in the theory. And that explains suppression patterns that you can see in observables. For instance, you can compute, well, people can compute the electron EDM or estimate it in the standard model, and you will see that it's suppressed by a bunch of parameters. So here, this product of 4 Fermis and masses, which arise from the mass differences that were written here. So the fact that you need all those coefficients at the same time to break CP has an impact on observable by saying how many parameters should appear to get a non-zero result. And since some of them are small, like for example, these masses or this product of CKM elements, because the CKM matrix has a hierarchical structure, that explains why some quantities are quite suppressed when it comes to CP violation. So you can do similar games beyond the standard model. So I won't review it here, but you have lots of references that did it for neutron masses, more Higgs doublets, supersymmetry, vector-like fermions, you name it. I haven't tried to list any because I was too afraid that I would miss people. But what I'm going to do here is focus on a specific kind of extension of the standard model, which is the SMEFT. And as I said, now the question that I'm asking is, when does the SMEFT break CP? Of course, we discussed that the SMEFT has a power expansion, so it technically has an infinite tower of gauge invariant operators, and one has to define an order at which you truncate to ask this question. And the question I'm asking this question on dimension 6. So I will stop when the cutoff appears with the power 1 over lambda square. And And okay, at this order, people have counted the number of coefficients that there exist. So here, if you're not familiar with the SMEFT, maybe all this doesn't mean much to you, but okay, here are the eventual numbers of real coefficients and imaginary coefficients that you find in any basis of the SMEFT. Please. Well, it's at the more general level, but I think I mean the expectation is that all of these quantities will have an observable effect. Yeah. Right. So. Yeah. Right. So no. So I will discuss both. Most of the talk will be about the general picture at the Lagrangian level, let's say, and I will discuss some applications for observables. Although most of the talk is at the generic level. I won't go into the kind of details you suggest. Yeah, I would say so. Yeah, I don't have any precise example in mind, but I mean, for instance, you could say that you could make this statement asking at which loop order this happens. So, for instance, this framework doesn't tell you at which loop order one invariant will contribute, for instance. So, yeah, I don't. Yeah, sorry, I don't have anything specific to say about this. But yeah, I think I agree with what you said. Yeah. Okay. Yes. Sorry, I was listing the number of independent quantities you find in the SMEFT at dimension 6, and usually those ones are dead CPodd. But in the light of what we saw from the standard model, I believe that it, for instance, to capture collective aspects of the theory or CP variation in the basis independent way, one would rather capture the CPodd quantities as Flavour invariants. Although, of course, in some basis, one can make sense of the imaginary part of this as violating CP. But Flavour invariants do this without requiring you to work in a given basis. So before I go on, you could object that the SMEFT breaks CP already at dimension 4 because we observed that the invariant for CP variation in the standard model is non-zero. So for instance, if you have this expansion, this SMEFT expansion of any amplitude in mind, the first term is likely to break CP. So it would sound meaningless to ask whether the next correction break or doesn't break CP. So in this slide, let me rephrase the question I'm asking. So the question I'm asking is really, what are new sources of CP variation that you find at dimension 6? So and this statement will become clear because when I define it as the remaining quantities that violate CP, if I go to points in the parameter space where this quantity is 0. So for instance, where this piece would not break CP. So this counting can be performed, and that's really the kind of objects I'm after. A second question I will be asking then is, how are they related to CP variation in UV models? So when I'm done defining this kind of objects, I will ask this question. And you could also ask, how large is the first mesh correction to CP variating observable? All these questions can be studied using the framework of CPodd Flavour invariants, which is what I will try to discuss now. Okay, so to discuss, as I just said, to discuss CP variation in the SMEFT, we think it's useful to discuss actually CP conservation in the SMEFT. So in this, seeing the SMEFT as an object with a generic parameter space. And one could ask, what are the sufficient and necessary conditions for the SMEFT to conserve CP? So here I haven't written it down again, but as I said, I work at dimension 6. So at the first non-trivial order at which the theory deviates from the standard model. Of course, since this, amplitudes and the question of CP conservation follow the EFT power counting. So first of all, if I want CP to be conserved, I have to have it conserved order by order. In particular, I need to impose this relation that the invariant at the level of the standard model itself is 0. So that singles out part of the parameter space already. And then I can ask what new conditions should I add to get CP conservation in the SMEFT. So the first question is, how many conditions am I after? How many conditions should I, how many conditions are sufficient for CP to be conserved? The naive expectation would be to take all these imaginary parameters that I flashed in the usual tables that classify SMEFT operators, but actually one can see that some imaginary parts are unphysical at dimension 6, although they are encoded in these dimension 6 operators. And the reason is that several of them are charged under lepton phase. Sorry, some of them change under phase redefinitions of the leptons. If they can contribute to observable, they have to do it in a way that is independent of this phase rotation. For instance, if you think of the electron EDM should not depend on which field I use to excite the electron, whether it's one field or I times this field. The notion of this electron EDM should not depend on that. And that means that if you take a combination of parameters that enter, let's say, EDMs, it has to do it in a way that is independent on this phase rephasing of the field. And since here I work at the first non-trivial order, I need to look for any coefficient here that would come from the SMEFT that has a transformation under this phase rephasing. I need to contract it with something at dimension 4 that would suppress, I mean, that would, how you say, form over an overall singlet object under this phase rephasing. And actually, if you look at the lepton rephasing, there's nothing at dimension 4 that does the job. There's no desarmable, there's no off-diagonal lepton coupling that would have such charges. So in that case, all the SMEFT phases at dimension 6, which are off-diagonal in leptons, cannot contribute at this order. So this is true up to one caveat, which is if you consider observables which are sensitive to neutrino masses. So for instance, if you consider all the set of observables which already have a non-zero value at the level of the star model, those must have a finite limit when the neutrinos contribute. So in particular, I cannot use the PMNS matrix which is charged under this phase rephasing to do the job. In the cases which for instance that would be sensitive to CP variation in the neutrino sector, that changes. So here I'm focusing on the observables, for instance, KNDKs or EDMs or all these observables which are non-zero already at the level of standard model and which remain finite when neutrino masses go to 0. So under this assumption, I think this claim is true. And the result is that in this table that I already presented, several of these coefficients turn out to be unphysical in the sense that they cannot contribute at first order in the SMEFT expansion. And when I carefully account for this effect, and I just look at the coefficients which are invariant under any of the rephasing of the electron fields, what I find is the reduced set of coefficients that I need to study. And this here, this 699, is actually the number I was looking for. So this is the number of all CPodd quantities I'm looking at, and that I need to send to 0 using such conditions. So in that case, this n would be 699. Here, something I haven't said is that here I really focus on the fermionic CP variation. So all the CP variation that comes from fermionic operating the SMEFT, which have at least 2 fermionic fields. So I have nothing to say about the bosonic ones, which are immediately invariant under the Flavour group. So here I'm really counting, you see, everything which is either bilinear in the fermion field or quadratic in the fermion field. Right. And this question of counting physical parameters actually also depends on the precise point in parameter space. So for instance, if you go to more degenerate cases, so for instance, for degenerate spectra in the quark sector, you lose some physical parameter at dimension 4, and again, you reduce the number of parameters that you can use to form invariance with the SMEFT coefficient. So for instance, if you go to this point in parameter space where the top and the charm and the bottom and the strange are degenerate in mass, then instead of 21 coefficient here, you will be down to 13 and so on. You can study this systematically at the level of the standard model to get all the possible numbers you expect in all the different points in parameter space. So that defines for you the number of quantity you need to set to 0 to get a CP conserving theory. So when you have all these, you can just go on and build invariants and try to see whether they are equivalent to the conditions you look at. But okay, sorry, I should just say that discounting of physical quantity can be performed for any number of generations. So for instance, when n here is the number of generations, this would be the change. So this first line here would be the usual numbers of the number that is usually worked out of independent coefficients. And this would be the physical one at dimension 6. So for a different case. for all the different observable, all the different operators of the SMEFT that you consider. Sorry, can you say it again? Well, not in these tables, but I mean, I can just add +1 to all these numbers here. But yes, yes. No, it doesn't. So here I'm looking for the new sources of CP violation. Yes. Yes, yes. Not in this table. Yes. Right. Okay. So okay, now I will try to build invariants which fulfill these conditions. First, I should probably discuss how in generic CPodd observable CPodd flavor invariant looks like. So for instance, you can take this specific SMEFT operator that couples two Higgses and left-handed quarks and ask what are the conditions for this operator to be CP violating. So you can go to textbooks which define the most generic CP transformation, for instance, here for massive Fermion fields. And you can work out the CP transformation of this operator. So under CP, it goes to itself times a phase, and CP is conserved if the Lagrangian is unchanged under this transformation. That gives you a condition on the different coefficients, and yeah, which is here. So another way to see is that up to this freedom here, which is so these phases are unfixed and they are related to how you can relabel the different fields. But up to these phases, it just means that a given coefficient has to be real. So another way to state it in words is that CP is conserved only if there exists a basis where this coefficient is real, and of course where the Yukawas are real, which I already assumed by choosing this this value for the standard model invariant. So that tells you how an CPodd invariant should look. The CPodd invariant is looking for something that remains imaginary in all bases. So it's the imaginary part of something that you can build that is invariant. Right. And so now that I define this, I can go on and look for this. And what we found is that there exist sets of linear flavor invariants which fulfill this this condition here boxed in red. So for instance, if you take this operator that I just mentioned, you can show that the theory, which is this theory, preserves CP at dimension 6 if and only if these 4 conditions are satisfied. That means that all the complex coefficients that you can find in this operator, which is Hermitian, are 0 in some basis. But that's the basis independent statement that you can make. So these are the usual Hermitian matrices you can build out of Yukawas. So you can check indeed these are 1 condition on the standard model plus 3 conditions on the SMEFT in the most generic point in parameter space. And for instance, if you go to this point I mentioned before, where the top and the charm are degenerated and the strange and the down are also degenerated, then these conditions actually degenerate to 1 plus 1 because these 3 different invariants collapse to a single quantity. And that is good because in our counting, we find just 1 quantity for this operator that could contribute at dimension 6 to any kind of observable. I should stress that this kind of behavior, namely that the set of invariants that you build reproduce all the conditions for CP conservation everywhere in parameter space, is not so trivial. For instance, here you can see that the invariants are built to look a bit ugly in the sense that you could, for instance, you could have defined something else, let's say with 1 less power of HD here, which looks different from this thing. But actually, if you did this, it would work in most of the parameter space, but not in this specific degenerate point. For instance, you would find degenerate points where you expect, let's say, two conditions on the different coefficients, and all this and this thing would collapse to 1. So finding a set of invariants which really correspond to the set of conditions you want to impose demands some kind of care. And for instance, this set of invariants do it for this specific observable, but not all the naive ones would. Right. So the fact that we found linear flavor invariants is actually is nice because it's consistent with the FT power counting in a trivial way. So there is 1 power of the SMEFT coefficient. So we expect a simple matching between observable at dimension 6 and this set of invariants. But it's not obvious a priori that you could do that. It's not obvious that every rephasing invariant linear quantity could be packaged in some number of invariants. And okay, but that happens to work. And this is nice because there are no subtleties associated to nonlinear relations. So for instance, in this paper, it was shown that at the level of neutrino physics, if you start to impose CP conservation for neutrinos using invariants, you could have like you could define an invariant which is a high degree polynomial in terms of the different fields that would indeed vanish at the point where CP is conserved, but that would have another zero somewhere else on the parameter space where CP is violated because of the nonlinear nature of the constraint. So since our constraints are all linear, these kind of subtleties do not arise. Okay, and such games are easily generalized to all SMEFT operators. So for instance, I mean, I'm not flashing the list of all the invariants you could build and which exactly match the number of conditions we expect from our previous counting. Okay, so that's all for I wanted to say about how we build those invariants, and now I will comment a bit on CP evaluation in the SMEFT using those invariants. So CP evaluation using those invariants must be CP evaluation must be proportional to invariants, simply because if they all vanish, there's no CP evaluation. So any observable has to be can be rewritten in terms of invariants. And as we said, for a given SMEFT coefficient, they encode collective effects, and they also encode suppression of CP valuating effects. So the best way to see it is to do an analysis a la Wolfenstein. So plugging explicitly the different hierarchies on the mass spectrum of fermions or of the CKM matrix. So here you use this parameter lambda, which is small, close to 0.2, related to the Cabibbo angle, and you can estimate the order in lambda that all the different masses have and all the different mixings have, let's say based on observations. So based on observation, that's the kind of suppression you found for masses or mixings. So you can plug this and estimate at which order CP is violated given the size of an invariant. So for instance, if you evaluate the usual invariant of the standard model, you get this suppression roughly up to some number under order 1 coefficients associated to the actual values of the mass and of the mixing. But the overall suppression is lambda to the 36. So that's another way to show a quantitative way to explain what I said before, namely that due to these collective effects and all the coefficients that enter CP violation, you have a strong suppression as soon as some of them are small, which is seen here when you evaluate this coefficient. You can do the same for invariants. For instance, for the 3 invariants we discussed just before, you can plug in the values. And if I assume that this coefficient is order 1, the first non-trivial coefficient happens at lambda to the 8. And the second one, which is not correlated to this first coefficient, happens at lambda to the 19. So that gives you an estimation on how small these coefficients could be when they contribute to CPodd observables. And studying the rank can also suggest how suppressed is the next independent effect. And you can also plug in some flavor assumptions in there to see how they change and how they could impact CP violation. So for instance, if you assume MFV, here I should probably, so in MFV, this coefficient then would be related to entries of the Euclid matrices and times some unknown flavor blind coefficient. So if you impose this ansatz of minimal flavor violation, MFV, you would see that the first non-trivial contribution to this invariance now is pushed to the order lambda to the 16. So these invariants give you a way of estimating directly algebraically, for instance, the impact of, let's say, flavor assumptions on these on CPodd observable. I should stress somehow, nevertheless, I should stress one important caveat to this is that the dynamics change the naive mass suppression that you find. So here I build invariants, and there are tons of powers of masses which contribute to it, and which also explain some amount of this suppression. So when you compute actual diagrams, you might not get something polynomial in masses. You might get logs, dilogs, or anything of this sort. That would change the naive scaling, and it happens in some examples that this scaling is conservative. Maybe you get something which is not it's too pessimistic. It gives you something. The actual suppression you get is relaxed because some of the masses that would contribute to this suppression actually turn into logs which are less suppressed. That happens in specific cases, but for instance, the electron EDM that we saw is one example of this, where there is one less power of the bottom mass compared to what you expect, although much of the suppression is still present. But there are cases where this does not happen. For instance, if you compute the RG running, so for instance, in this paper, these authors computed the RG running, the contribution to the running of the electric dipole moment of the electron from the SMEFT operators. So if you look at the leading log contribution, this all the UKRs enter as coupling, vertices coupling, and the suppression you work out here is actually correct. And there are other examples. For instance, if you look at again at observables which should not have a which have a well-defined behavior when the masses are sent to zero, quark masses are sent to zero, for instance, in from EDM. Then the first estimation of the suppression you can do, for instance, from the first non-trivial order in this invariant is also something you can use. Right. Okay. Something else I would like to say is that, so I said that the CP violation in the SMEFT is proportional to invariance, but you could ask which one. In particular, so here I discussed the contribution of the new CPV quantities in the SMEFT, but the standard model, the variation that comes from the standard model could interfere with the SMEFT coefficient. For instance, if you have loops over 3 generations and with electrolytic couplings and some SMEFT vertices, what you could get is something that violates CP because it's sensitive to the phase in the standard model, and that interferes with another coefficient of the SMEFT, which might not be part of the ones we associated to new sources of CPV. However, as is seen from this sentence, you need something specific in terms of diagrams to get such an expression. You need something, for instance, that is sensitive to 3 generations at the same time. Otherwise, it won't be sensitive to the standard model CPV. So if you take simple enough processes, let's say, then that contributes to CPodd observable, then they will map to this new source of CPV. So for instance, again, if I use EDMs as an example, there are those famous bar Z two-loop contributions to the electron EDM. And here in this loop, there's no, each of these diagrams can be sent independently of different flavors. They are not sensitive to the fact that you have 3 generations. And this, when you take a look at the result, the different quantities that enter in the result. So here, sorry, I should have said that to get this effect, you need a dimension 6 contribution to the up type UKR, which takes this form in the SMEFT and which enters this, well, in that case, this vertex of the diagram. When you do this, then this vertex that used to conserve CP in the standard model now has a part that does violate CP. And the result is an electron EDM that has this expression. So here, this is a function that I'm not showing that depends on dialogues. But the thing I want to stress is that the different coefficients that contribute, so the thing that all the parameter space that enters into this computation is actually captured, is actually in one-to-one corresponding with the invariance we discussed. So there's no interference between the standard model CP violation and CP even effects in the SMEFT, because there's no, only generations contribute one by one. The same happened for similar diagrams, similar contribution to the electron EDM. For instance, if you take this kind of loop where I have two W contributions, similar bar Z kind of diagram, you also get an expression which depends on, which has this expression. Again, this is a complicated function of the masses that I'm not plotting, but I'm just emphasizing that the part that depends on the SMEFT coefficients, although it has some non-trivial interplay with the CK matrix, is also in one-to-one correspondence with this invariance we built. Okay. Yeah, and you can see already at the level of this example that the new sources of CPV should not be taken to be aligned with the imaginary part in whatever basis you choose. First of all, because the fact that I said whatever basis means that imaginary part is not something that is well defined. And here you can see it. If you work in some bases, which are the usual bases, for instance, the one where the CK matrix is complex up to the 3-2 entry, I think in that case. This new source of CPV that we capture in invariance is not aligned fully with an imaginary part. So here the 3-2 entry of this coefficient. So sorry, yeah, here this is the operator in the SMEFT that changes the W coupling, the 3-point coupling between up, down, and W fields. So the new source of CPV contained in this coupling is not aligned with the imaginary part. It has one leg into the real part, but nevertheless, it corresponds to one of these invariants we built that are important to capture new sources of CP. Well, yes, but I would say no. I would say that, so the statement which is clean to make is the statement where CP is concerned with the standard model. When CP is concerned with the standard model, then there are some directions which are well defined that violate CP. Yes. Well, okay. Okay. So yeah, actually, no, I think this what I want to emphasize is probably precisely this point. So if okay, here I probably should have, then to answer your question, I should have shown the exact dependence. Here I just shown I use this Wolfenstein parameterization just to show which entry contributes and at which order. I could reconstruct the complete analytic dependence of this entry. What you would see here is that the analytic dependence of this entry is not aligned with the thing that should vanish when CP vanishes in the standard model. For instance, there are parameter points where CP is concerned with the standard model, and this thing remains. Well, then of course you can go to another basis where this thing vanishes in that case, but that's another basis. That's a matter of defining the imaginary part in the good basis. But if I stay in the same basis and I send the order parameter of CP variation of the standard model to 0 in some way, there are some ways that leave this thing untouched, for instance. Yeah, but it's not always. Yeah. Well. Yes. Okay. Yes, I agree with if I do what you just said, I will indeed get. So okay, I work in a given Flavour basis, and I send this phase to 0. Indeed, in this Flavour basis, my new sources of CPV are aligned with this remaining piece. Yes, absolutely. What I'm saying is that if I now, so I use this previous discussion where CP was concerned with the standard model to somehow have in mind how I could redefine all the parameter space of the SMEFT in terms of Flavour invariance. And I would like to define the CPodd quantities in terms of quantity, which when CP is concerned with the standard model are indeed aligned with the quantities I want to send to 0 to get CP conservation in the overall model. But now that I work with observables, I still keep these directions as being the one that I call new sources of CP, but I turn on a non-zero phase in the CKM. So when I do this, I can still evaluate these directions, and these directions still can be sensitive to the CKM. However, that doesn't mean that this quantity is an interference between standard model CP variation and something that does not violate CP. So this is what I get when I evaluate simply my invariance, my new sources of the invariance I define to be my new sources of CPV. If I evaluate them in one basis where the CKM phase is non-zero, I get this expression. But that doesn't tell me anything about what happens at the level of CP. So that doesn't tell me anything about whether CP is violated or not in the standard model. So for instance, I could get CP conservation by sending this phase to 0. That's true. But I could do it in other ways. I could get CP variation in the standard model by sending a mixing angle to 0, or by taking two masses degenerate, something like this. And in all those cases, this would remain as it is. In some of these cases, there are some mixing angles which enter here, but some which don't. So that shows that the thing that enters this piece is not all the order parameter of CP variation in the standard model times something else. It's something different. And I can just check that when I evaluate my invariants that are aligned with the new sources of CPV, this is exactly the contribution I get. In some bases, it will change. I can rotate imaginary part and real part into one another. That's doable, and I will change this this expression. But in this particular basis, which is the usual basis that everybody uses, like with a CKM matrix that is mostly real up to one phase, which is off diagonal in the 2-3 entry, that's how my new source of CPV evaluates. Is this answering your question? No, I think it's an important question that you're asking. But yeah. Yes. Yes. Sure. Yeah. Yes, I see what you mean, but yes, yes, yeah. Sorry, yes, yes, yes. Yeah, well, I agree with you on this point. Okay. Yeah. Okay. Okay. Let me just say one final thing, and then I go. Yeah. Okay. What this expression shows is that there is some kind of ambiguity in how you define CPodd quantities when the standard model itself violates CP, right? Because you could add something that violates CP, any kind of thing that multiplies the source of CP oddness in the standard model. Yeah. Yeah. Exactly. Yes. Yes, indeed. Right. Yes, absolutely. Yeah. Okay. Sure. Okay. Then what I'm saying is that the expression I worked out from this, I mean, this approach that I define to define CP conservation condition, these invariants that I define are sufficient to capture this quantity. That's what I'm saying. I don't need to know other parts of the parameter space that would be CP event, for instance. I just need to know this quantity that I define. And now I just evaluate it at the physical point where CP is also broken in the standard model. What I say is that this new quantity that I define is sufficient to capture all these different entries. But indeed, it has an expression that is not aligned with this, as you would expect. But it would, of course, be aligned if I remove CP variation from the standard model. Yeah. Okay. The final thing I wanted to say about these invariants is that they're allowed to easily track CP violation. And what I mean by track is to match to see how CP violation is transmitted from UV models to the SMEFT. So the example I would like to discuss is the case of it's a simple model of spontaneous CP breaking, which actually I forgot to put a reference for. So it's I think it's a paper of Branco, Silva, and probably others. Yeah, sorry. Okay. Okay, the model is the following in the UV. You have an extra vector-like D quark and a new scalar. So there is a point in this parameter space. And so this is the Higgs, and the rest are cupping constants. So F prime, and gamma are new cupping constants. So there is there exists a point in parameter space such that this model preserves CP. So you can choose this point in parameter space, for instance, the point where gamma and F prime and mu are all real here. And the theory will spontaneously break CP if you give if the minimum of the scalar potential, which I'm not writing here, which is studied in the original paper, is such that this scalar S has an imaginary value, a complex value. So if you do this, you have a theory which does not break CP in the deep UV, but which does in the IR, and you can match this theory to the SMEFT. So you can integrate out the scalar excitation in S and the vector-like down quark. If you do this, you match to the SMEFT. Here, for instance, you can do it using this this trivial matching paper of the Granada group, which I also forgot to cite here. And you get the following observable. So for people who are not used to SMEFT, sorry, so this is a modification to the down quark Yukawa. So the same structure as the down quark Yukawa times the Higgs square. And this is an observable that modifies the Z. So this is an operator that modifies the Z coupling of the left-handed quarks and the W coupling of the left-handed quarks. So that's the SMEFT you get, and the parameters are expressed in terms of the UV parameters. So this lambda coupling here is written, well, it has the following expression in terms of the UV coupling, where this curly F is defined as follows, where alpha is the phase in the scalar wave, and the Yukawas are what they are, and this Y up is the same as in the UV, but this YD is generated by this mechanism and has the following expression. So in this expression, it's a rather complicated expression. For instance, if you want to go to the basis, that is the usual basis where you have diagonal mass terms and the CK matrix, you have to define rotation matrices, which are defined somehow, well, if you want to, they don't have a full analytic expression in terms of the original parameters. They just exist via usual matrix algebra, but you cannot write them explicitly, or at least in a simple way, let's say. So for instance, tracking down how the CP violation is transmitted to the SMEFT using this parameter from the UV parameter is not so easy. You have to diagonalize, go to the mass basis and match to the thing you usually know. So for instance, the CKM phase. However, if you do it with invariance, it's a matter of one-line computation. So for instance, if you ask the question, what makes CP conserved at dimension 4 or at dimension 6 in this model? So which part of the parameter space happen to preserve CP if I just truncate at the level of the SAR model, which parts violate CP if I also include dimension 6 and so on. So this check can be performed algebraically and really in one line when you use invariance. So for instance, you can see that you can find parameter points where J4 is 0, but not the L's. So these invariants at dimension 6 or vice versa. So for instance, you can see, you easily see how this one phase, for instance, correlates with the different collective effect to induce CP variation at the level of the SAR model or the level of the SMEFT or both together and so on. So these kind of things, which would be hard to work out at the level of this Lagrangian, you can find them immediately in this. I'm not showing precise values, but you can ask me. Okay, so that brings me to the conclusion of my talk. So hopefully I managed to explain that we revisited the counting of physical parameters in the SMEFT at dimension 6. So I explained under which assumption that was valid, and so that leads to some observables, some coefficient of the SMEFT, which cannot enter the first BSM contribution to CPV observables, to observables in particular, and to CPV observables, sorry, to observables in general, and to CPV observable in particular. And with this, we build, focusing on the CPodd physical parameters among those ones, we build Flavour invariants which capture all of them. So which we would define as basis as at least, that would be our proposal to define basis independent direction parameter space that are associated to CPodd effects. And as I tried to argue at the end, they can be used to identify collective aspects of CPV, which you can work out by looking at the algebraic expressions, which are unfortunately too ugly for me to show and extract anything in this talk, but you can do that. You can evaluate level of suppression of CP breaking, as I mentioned. And you can also study how CPV is transferred from UV models to the SMEFT. So for instance, you have objects which can be directly evaluated on the UV parameters to get numerical answers, and do not depend on you going to the right IR basis to match to what you would usually use from a bottom-up perspective. And okay, maybe there are other applications. We are still working this out, and if you have any idea. Thank you for the attention.
Are there any questions or comments?
No, we haven't. It's something we would like to do. We haven't really started, so I don't have anything precise to say, but yeah. So something we would like to work out are indeed so you can work out the invariant, sorry, the renormalization group at the level of these invariants. For instance, this was done recently for neutrinos. Okay, I'm not probably for other things, but at least for neutrinos. And yeah, you could do the same here. So for instance, look at the renormalization flow of invariants into other invariants. And so for instance, that would be a nice way to check that the basis is complete, for instance, to show that you don't generate new structures via renormalization group. But no, we haven't. This is something that is yet to be done. Sorry, was this your question? Or? Okay.
Other question or comments?
So how many Flavour invariants you have?
699. Yeah.
Okay, so one question. Imagine that fix the CPM matches, that's real.
Yeah.
And then would it be possible to get more than CP results just from basis coming from all these 600 sources?
You mean could I like mimic the thermal?
Yeah.
I don't know. Yes, it's also something.
Because
Yeah, no.
our analysis was supposed
Yeah.
that CPM was there and just adding some sources.
Yeah.
To which extent is assumption very strong.
Yeah, I understand. Yeah, indeed. I mean, this analysis. So this definition of CP, of these new sources of CPV is independent. I mean, it's an analysis that we perform at the taking the SMEFT as being a mathematical theory, right? It's full parameter space and working out the point where CP is conserved and turning this into conditions on invariance. So, I mean, this list does not depend on any assumption about what is the physical point realized in nature. Then indeed, in the different evaluations that I performed, I was assuming, I was plugging in the values that are measured. Yeah, indeed. And that's an interesting question. We haven't really looked into it. Something we mentioned, but we haven't looked into it yet. So yeah, that's definitely an interesting question. Yeah. Right. Yeah, indeed. Yeah, especially in many observables. Yeah, in many observables, the CP variation is very faint. So indeed, there may be some room for sure. Yeah. Yes. Yeah. 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 Yes, yeah. Well, yeah. Well, so I know I don't know all the bounds. Yeah, I know, for instance, that to remain, I mean, for instance, the group of Bourras et al. Evaluated, for instance, how large the cutoff should be to, for instance, for the epsilon prime or epsilon parameter to remain within the, sorry, for the SMEFT contribution to be within the error bars of this contribution and this coefficient, which I forgot what it. So I think, yeah, the bounds were around the TV and the error is, I'm afraid to say something wrong, I would have said at least 100 or 1,000 of the original result. So maybe, for instance, for this kind of observable, it would be hard, although it was on a one operator by one operator basis. So maybe there's still some room. I don't know. Yeah, that's something. Yeah, that's an interesting question. Yeah.
You were considering only left number, variant number conserving operators.
Right. Yeah. Indeed.
So
yes.
the PMNS matrix, you're not discarding it at all.
No. Yeah. As I said, when you plug in the PMNS matrix in the game, first of all you enlarge the number of coefficients that can contribute. However, since the neutrino, so for instance, if you want to work out to estimate how large the PMNS matrix contribution could be to an EDM, sorry, let me rephrase. If you want to evaluate how much the PMNS could help something that I called in physical dimensions to contribute to an EDM, this is a question you can ask. If you take the extra EDM, for instance, you know that the PMNS matrix has to come with an extra neutrino mass. So the neutrino mass, for instance, if you count it as coming from the Weinberg operator, it's something already next order in the EFT. So in some observable, this PMNS matrix won't change at the result at leading order. If you now look at observables which are really sensitive to neutrino masses, there's no reason to have this mass suppression, and then that's another story. Yeah, but this we haven't looked into. Yeah, we have restricted to these observables where we have a handle on how the neutrino masses can contribute, and they make it. They enter in a way that makes it next order in the EFT. At least they interplay with these dimensions.
Is there any question or comments for people from Zoom?
Okay.
Yeah, sorry.
Yes, yeah, you could. You mean the theta QCD angle, right? This kind of yeah. You can do this. I don't know. So for instance, I had this slide hidden about theta QCD. So you can ask this already at the level of dimension 4. So for instance, there are phases that you could ask if I now. So there are phases which are charged under the U1 part of the Flavour group, and you could try to make invariants. So far, I built invariants which are invariant under the full Flavour group, including the U1s, by taking these traces. You could use similar other kind of structures with determinants or epsilon tensors, which are now not invariant under the U1s. And then you could use the theta angle to offset these transformations and build new kind of invariants. So for instance, if you do it with theta QCD, you get a new object element that comes from the Summer Lagrangian that has transformation that can help you to build new invariants. First of which, there is one CPV observable, CPV invariant at the level of standard model, which is the famous one. And you can build other things. For instance, you can build this horrible expression where this is a 4-family operator with 2 Qs, 1 U and 1 D. This horrible expression will, for instance, would be a candidate of an invariant that would be associated to strong CPV contribution to CPV observables. So yeah, you can do this. So we just played this game so far with theta QCD. With theta QCD, you get no new phases that contribute, but you get new structures, let's say. So for instance, we check that the things you can build, for instance, with theta QCD are super suppressed in the UV. For instance, yeah, if you dress them with the usual non-perturbative action of this fault in the UV, something super small. However, these things could be relevant in the IR, for instance. Yeah, they could contribute to in the IR the CPV that comes from this theta QCD could compete with the ones I worked out. Yeah. So that's the answer about theta QCD and how that works out with the next correction in the SMEFT. We haven't really worked out yet, but that's something on our table indeed. Because you could, for instance, this theta has also a power expansion in the SMEFT that you can work out, and the same for electric angle. Yeah, I know, it's something we'd like to do.
Well, if there's no other question or comment,
sorry, but you have.
Then I think that the time is okay for thanking again the speaker.
Oh, thank you.
Yeah,